So good afternoon, everyone, and welcome to Lecture 3 of 124104, Physics 1A. We are continuing on from where we left off, as well as learning about vectors. So before we go to vectors, when we go to vectors, we will mostly focus on vector maths, vector operations. How do we add and subtract vectors? And what happens if we multiply a vector with a number or a scalar quantity. But before we go to vectors, let's continue what we were talking about in the previous lecture. So previously, we tried to describe an object that is moving. And we defined and differentiated these terms from each other: distance, displacement, speed, velocity, and acceleration. We also started to look at how we interpret motion graphs. We said that the motion of an object can be plotted in a graph, for example, this position versus time graph here. And we learned last time that if we calculate the slope of this graph, we are able to get either the distance if we are talking about speed, or the displacement if we are talking about velocity. So we can do the same thing if we are given a graph that shows the velocity of an object in the y-axis, right? So like this graph shown here, the y-axis is velocity in meters per second, and the x-axis is time in seconds. If we calculate the slope of this graph, slope being defined change in the value of the y-axis divided by change in the value of the x-axis, right? And if we substitute what the x and y-axis represent, the change in the y-axis will actually be the change in velocity. The change in the x-axis will be the change in time, right? Change in velocity, of course, is defined as final minus initial velocity, and likewise for the change in time, final minus initial time. So if we work out the equation for finding a slope, we then come up with the definition, the change of velocity over change in time, which is consistent to what we learned as acceleration, right? So if you are given a velocity versus time graph and you get the slope of that graph, then effectively you are calculating the acceleration of the average acceleration of the object's motion. Right? Last time we also looked at how we can deal with motion graphs that are curved. The only difference last time was the x-axis was position. This time the y-axis was position, and this time the y-axis is given as velocity. Right, so what do we do if we're given a curved graph? Again, the key idea with motion graphs and slope is to pick up 2 points along your graph and use those 2 points to calculate the slope, and that will give you the average quantity, in this case, average acceleration. Right. So say, for example, we're being asked to find the average acceleration between the time interval 0 and 70 seconds. Then we pick these 2 points here, right? We'll know that at 70 seconds, the velocity changed by this much. And of course, the time interval is 70 seconds. We can then calculate the slope using these 2 points along the graph, and that slope will give us the average acceleration. And it was the same method as what we looked at before, except that if the y-axis is position or displacement, then the slope will give you average velocity. Right. For instantaneous acceleration, Again, recall when we say instantaneous, it's the acceleration at a single time, at a single, at an instant of time. So we are looking only at a single point. We want to find the acceleration at this instant of time around, if you project that here, that will be around 28 seconds, for example. Okay, we also use the same strategy. We already learned this strategy before when we were looking at the position versus time graph and wanting to find the instantaneous velocity. Right? What you have to do is to draw a tangent line or a straight line that passes through the point where you want to find the instantaneous acceleration. And then you use this tangent line to pick up 2 points along this tangent line to calculate the slope, its slope, and therefore determine the instantaneous acceleration, right? So in this particular diagram, this bold black line is the tangent to this point we want to determine the instantaneous acceleration. And then the endpoints, these 2 points were used to determine the change in velocity and the change in time or time interval. We use these 2 points to calculate the slope. That will give us the instantaneous acceleration. Right? And the steeper the slope, the larger the acceleration, because the steeper the slope, the bigger the change in velocity. Right? Okay, so just a quick conceptual question here to illustrate the point about instantaneous acceleration. We have here 2 graphs, the red graph, which is straight, and then this black graph that's curved. We want to find at what time is the instantaneous acceleration the same for the 2 moving objects whose graphs of motion are represented here. And you have here choices for the times: 1 second, 2.5, 4, 5, and 6.5 seconds. Or do you think that their instantaneous acceleration will never be the same? Right, so the strategy to use here, because we're looking at instantaneous acceleration, we then have to look at each instant of time that's given in the choices, right? 1 second, draw a tangent line, okay, at that point, and do that for each of the times: 2.5, 4, 5, and 6.5 seconds. So you have each of the times you want to determine the instantaneous acceleration of the curved motion graph and the tangents or tangent lines at those particular times. Notice that if you have a straight line, right, and you also look at those particular times given in the choices. If you have a straight line and you try to draw a line tangent at that point, notice how the tangent line will follow the straight line itself. So if it's a straight line graph, you actually don't need to draw a tangent line because the tangent line will follow that straight line graph anyway. And you can just right away calculate the slope of that straight line graph. Okay, so just looking at the tangent lines here, which time do you think will the objects have the same instantaneous acceleration? Right? The slope of the graph will give you the acceleration. Hence, if the acceleration was the same, then the slopes should be the same. And you know, at this time here, 2.5 seconds, the slope or the tangent to the point at 2.5 seconds is parallel. The two slopes are parallel for both graphs. Okay, so at 2.5 seconds, the objects will have the same instantaneous acceleration. Okay. Good. So from here, we saw that given motion graphs, we can determine a kinematic variable or a physical quantity that describes the object's motion by calculating the slope of that graph. Whether we get acceleration or velocity depends on what value is at the y-axis of that graph. Given a motion graph, we can also determine some kinematic variable or physical quantity that describes an object's motion by calculating the area between the graph and the horizontal axis. Just like with slope, the quantity that the area gives us depends on what quantity is at the y-axis. So for this particular motion graph, where the y-axis is given as velocity, of course, the x-axis is time, the area between the graph and the horizontal axis will give us the displacement of the object. Okay. Right? Just some conceptual, just some concepts here. If the area is below the horizontal axis, just like here, so the graph here is the blue line, right? So if you get the area of this part of the graph, notice how that area is below the horizontal axis. That will give you a negative displacement because, of course, numbers less than 0 will be negative. Whereas if you get the area, for example, of this part of the graph, it will also give you displacement, but notice how the area is above the horizontal axis. Okay, and of course, numbers above the horizontal axis are positive, then therefore this area should give you a positive displacement. Okay. The positive and negative signs that you get sort of indicates the direction for which the object moved. Okay. So positive, as we said, moving to the right or moving upwards, negative, moving to the left or downwards. Okay. Right, if the y-axis is given as acceleration, just like these graphs here, the x-axis is sort of always time in motion graphs. Right? If the y-axis is given as acceleration, then the area between the graph and the horizontal axis will give you the change in velocity of the object. And likewise, as in displacement that we've seen earlier, if the area is above the horizontal axis, then the change in velocity will be positive. And if the area is below the horizontal axis, then the change in displacement, change in velocity will be negative. Okay. The only real complication comes when you have a complex graph, just like this graph shown here. Right? So this graph consists of, if you want to get the area of this graph, notice how it consists of polygons that sometimes have complicated shapes. But remember that, right, that any area can be broken down into triangles and rectangles. And by breaking down a polygon shape into triangles and rectangles, that allows you to calculate the area more simply. So for example, it's easy to see the area here is a triangle. But for this part of the graph here, you can easily break that into triangles and rectangles, right? And then calculate the area of each of these portions here, add them all up, and that will give you the total or net displacement, right? We know that the area will give us displacement because the y-axis is given as velocity. Okay, so since we'll be calculating the areas of a triangle, a rectangle, just this slide just gives like a refresher of how do we calculate the areas. For a rectangle, it's simply length times width. For a triangle, regardless of the kind, whether it's an isosceles right triangle, right? As long as it's a triangle, you calculate the area as 1/2 base times height. There's another shape that is useful to know the area of, and it's the area of a trapezoid, because you can also divide a graph into a trapezoid. Of course, a trapezoid can be divided into a triangle and a rectangle, in which case you need to calculate two areas. But if you know the equation for finding the area of a trapezoid, that sometimes simplifies the calculation because you just need to calculate the area of a trapezoid instead of calculating the area of a triangle and a rectangle. So the equation for the area of a trapezoid is given here, 1/2 height, base 1 plus base 2. So to define a trapezoid, you need two sides that are parallel with each other. Okay, those two parallel sides are called the bases. You have base 1 and base 2, and the height is the distance between those two bases. All right, so let's look at this example here. You have a velocity versus time graph, which is this bold black line here, which describes the motion of an object. You want to determine its displacement between 11 and 14 seconds. Right? We learned that if you have a velocity versus time graph, to find the displacement, you need to determine the area between the graph and the horizontal axis. We just want the displacement at this time interval. So we just want the displacement between 11 and 14 seconds, right? Which means that we need to calculate the area right, of this portion of the graph, the area between the graph and the horizontal axis. Okay, examining the shape formed by this part of the graph whose area we want to calculate. Notice that it's a trapezoid, right? You have two sides that are parallel to each other, therefore giving you two bases. And then the distance between those two parallel sides defines the height of the trapezoid. So the area of a trapezoid, okay, is 1/2 times the height times the sum of the bases. So if you do the calculation, the height will be the distance between these two parallel sides. That will be 14, take away 11, will be 5. Oh, sorry, 3. Don't know why I said 5. 11, 14 take away 11 is obviously 3. The height is 3. And then the bases are defined by these parallel sides. So you have 5 meters per second for one side and 10 meters per second for the other side. So you have 5 plus 10. Carrying out the calculation gives you a positive 22.5 meters. So that is, yeah. in the end, don't forget to include the unit, because the unit will then define what kind of quantity 22.5 is. So the displacement between 11 and 14 seconds is 22.5 meters. You came up with a positive number, which means that the displacement was either to the right or upwards. It was not really specified in the problem, but you can also do a quick check by looking at the area here. Notice how it's above the horizontal axis, and therefore you would expect a positive displacement for this motion graph. Right? Any question about that? Or hopefully it's pretty straightforward enough. Okay. As always, if you have any question, please pop it in the chat box or speak directly at any time during the lecture, and I'll be happy to answer those questions. Good. All right, so here I just summarize, I give a table summarizing, the different motion graphs that you might encounter: displacement versus time, velocity versus time, and acceleration versus time graphs, and which quantities, kinematic quantities, you can determine by solving the slope and the areas of these motion graphs. Okay. So I think this will be a very useful slide to refer to, for example, while you're doing the assignments, and as well as the tests. So the tests are actually open book and open slides. So you're free to refer to the lecture slides while you're doing the test. And maybe this graph, this table here will be quite useful to sort of know whether you have to calculate the slope or the area if you're being asked to determine velocity, acceleration, and displacement. Right? Okay, so what we have learned so far is that we have defined the kinematic variables, or the quantities that describe an object's motion. We then learned how to interpret a motion graph that contains these kinematic variables, or these physical quantities describing an object's motion. We learned that if you get the slope and the area of the graph, you come up with an unknown kinematic variable or equation, kinematic physical quantity. But as you can imagine, right, even though you can use the motion graph to determine, for example, the acceleration, in this case of this velocity time graph, or to determine the displacement from this velocity time graph, using motion graphs can become quite tedious, especially and also inaccurate, especially if you're having to estimate, for example, points, right, and read off your graph estimates of points. So there's another way of determining different kinematic variables that describe an object's motion, and these are called kinematic equations. The kinematic equations are actually derived from the motion graphs. We will not do the derivation in this course. If you're interested in looking at the derivations of these kinematic equations, you can always refer to the textbook. But essentially, these kinematic equations describe the kinematic variables by relating them with each other. Okay. And this slide lists down the five kinematic equations of motion that relates the displacement, time, velocity, and acceleration with each other. You don't have to memorize these kinematic equations, although if you want to, you're welcome to do so. There's no one stopping you. But it's important to know what each of the variables in these equations mean. Okay, because of course, if you use these equations in problem solving, then you have to know what each of the variables mean. So I've listed down here each of these variables. Okay, the subscript I means initial, subscript F means final, and when you have delta, the Greek symbol delta, then that means change or final minus initial. Right. So using these kinematic equations, a note here that the kinematic equations are only valid if the acceleration is constant, but I guess you don't have to worry about that because in this course, we will only consider motion with constant acceleration, meaning these kinematic equations will always be valid whenever you need to use them in this course. Okay? But using these kinematic equations is pretty simple because as you can see here, each of the kinematic equations will always contain 4 out of 5 kinematic variables, right? If you can see here, the green tick marks will tell you which variables are contained in a particular kinematic equation. The red X's tell you which variable is missing in a particular kinematic equation, right? So therefore, by looking at what variable you know, what variable is what variable, kinematic variable is given in the problem, what kinematic variable you are asked to solve, it's then a matter of picking from these 5 equations the most sensible equation to use to solve for what's being asked. And we'll look at that example of how to use these kinematic equations, right? Just some hints because usually when you are required to use kinematic equations, the problem comes in the form of worded problems. And sometimes it's useful to know some kind of vocabulary hints. For example, if you read in the problem that the object starts from rest, okay, we don't explicitly say that the initial velocity is 0. We just say that the object starts from rest, but that means that the initial velocity is 0. Okay. If the object stops, it means that the final velocity is 0. Okay, if we say the object falls vertically, or the object is free falling, or assume that there's negligible resistance, then it means that the acceleration is negative 9.8 meters per second squared. I mean, we will not, we sometimes or often, we will not explicitly say that the acceleration is negative 9.8 meters per second squared, but you will often read in the problem something like the object falls vertically downwards, assume negligible resistance, in which case it is understood that you should know that the acceleration is negative 9.8 meters per second squared, which is called the gravitational acceleration g. And we'll talk more about the gravitational acceleration g in the next slide. Okay, but to round off this slide about hints, if you read the word drop, it means that the initial velocity is 0, because it's sort of like the object started from rest and then it was dropped, so it's implied that the initial velocity is 0. All right, so let's talk about that G, that free-falling negligible resistance case where acceleration is negative 9.8 meters per second squared. Right, that particular type of motion is what we call free fall. So it's a special, it's motion under a special condition where it's assumed that the object is moving because of gravity only. So this usually a very good example is when an object is dropped from a certain height. Of course, everyone knows this object will fall to the ground because of the gravitational pull on the object. Okay, so the object will fall because of gravity. The assumption that we're making is that the air resistance is negligible. Okay. So if the air resistance is negligible, then the object will fall, will fall such that any object falling under the influence of gravity without air resistance will have the same acceleration. Okay. Right. The acceleration that each object will have it's called the gravitational acceleration. It's 9.8 meters per second squared. What does that mean? Right? Recall that acceleration is change in velocity over change in time. So that means that every second, the velocity of the object changes by 9.8 meters per second. Okay. If the object is moving upwards, it means that its velocity is decreasing by 9.8 meters per second every second. If the object is falling downwards, its velocity is increasing by 9.8 meters per second every second. Okay. So that's what acceleration is 9.8 meters per second squared means. The velocity changes by 9.8 meters per second every second. And it's constant for any object that's falling on Earth where air resistance is negligible. Okay. Right. Acceleration is a vector quantity, so it should have a direction. We know that the gravitational pull is always downwards, and therefore the direction will always be negative. So the gravitational acceleration will always be negative 9.8 meters per second squared. Okay. Right. Because free fall is such a special kind of motion, there are in worded problems, you can also pick up hints as to what the values of some kinematic variables are. For example, falls vertically, free falling, or negligible resistance under vertical motion means automatically that acceleration is negative 9.8 meters per second squared, right? As I mentioned, dropped or released means initial velocity is 0. When an object is thrown upwards, okay, you have this object here, it's initially at rest, okay, and that's why, initially at rest. But in order for it to move upwards, you'll sort of have to apply some initial velocity. So in an upward, when an object is thrown upwards, the initial velocity is always non-zero with the direction of upwards or positive. Okay. We all know, of course, that any object that's thrown upwards will eventually come down. Okay. So it will eventually reach some peak height and then come down. Before it comes down, it momentarily stops. And so the velocity at the top of its vertical motion will always be 0. Okay? So we can then take the final velocity at the top of the object's motion to be v final is equal to 0. Okay? Because the object is being pulled by gravity at the time it goes up and also at the time it goes down, the time to go up should be equal to the time to go down to the same starting initial height. Okay. Right? When an object is thrown down, When an object is thrown down, the word throw means that some initial velocity was applied in order for the object to move downwards with some initial velocity. Of course, it's moving downwards, so the direction, the sign of your initial velocity should be negative. When it's thrown downwards, we can also say that the initial position will be the zero position, and hence the displacement will be negative. Right. So just a distinction here, if we say thrown downwards, it means non-zero initial velocity. It's different when the object is dropped. When the object is dropped, it's essentially released, and that's when initial velocity is zero. Okay, so a little bit care about vocabulary can be useful in this case. When the object hits the ground, this is a common misconception I see all the time. When the object hits the ground, it doesn't mean that the final velocity is zero. Okay? If you, I don't know if you can see this, maybe this is better, yeah. If I drop something from a height, it doesn't really stop, or you can try and do it. Drop a pen on your desk. Notice how when it hits your desk, it doesn't really stop abruptly. Sometimes it bounces off, but it still has, it's still moving somehow. So the final velocity is not zero, and often we ask for you to solve this final velocity. So for this course, there's a question here. For this course, we will often use 9.8, okay? Unless we want to give three significant figures, in which case we'll use 9.81. But if we don't give the explicit value for G, you can assume 9.8 to have two significant figures. Okay, so let's look at this example for free fall. A ball is thrown vertically upwards with an initial speed of 30 meters per second. We assume negligible friction, and we want to find in which direction and what speed is the ball moving after 2 seconds, and how high would the ball go before falling back down. Right, can be useful to visualize what's happening to the ball. Right, you have this ball, it's thrown upwards. Right, thrown upwards, the initial velocity is given 30 meters per second. So of course the ball will move upwards because it's thrown upwards. We know from free fall that the velocity of an upward moving object will decrease by 9.8 meters per second every second. So after 1 second of being thrown, right, the velocity of the ball would have decreased by 9.8 meters per second. Just for this particular illustration, let's just round 9.8 to 10 because it's easier, to subtract whole numbers. Right? So if we assume that the 9.8 is rounded to 10, that means that after 1 second, the velocity of the ball will be 20 meters per second. It would have decreased by 10 meters per second every second. So that after 2 seconds, the velocity will be 10 meters per second. 3 seconds, the velocity would decrease a further 10 meters per second. And then we see that it's 0 meters per second after 3 seconds. At which case, it has no more velocity to go further up. So it starts to fall back down. Okay, the time it takes to reach the top will be the same time it takes to reach the same initial height, because again, gravitational pull is constant. After 1 second of falling down, the velocity of the ball would have increased by 10 meters per second, right? And then another second will result to 10 meters per second of increase in velocity. After another second, the velocity would have increased by another 10 meters per second. Okay. Right? When going down, the signs for velocity is negative because the direction is downward. Okay. So sort of this illustrates, this is a visual representation of the free fall problem, which then facilitates us to answer this question. Okay, after 2 seconds, right? If we know the concept of free fall, we don't even have to use kinematic equations. After 2 seconds, we know the ball is moving upwards with a velocity of 10 meters per second, right? Estimated because we rounded 9.8 to 10. Right, let's try to answer this question using kinematic equations, just to demonstrate the use of them, right? Okay, so in kinematic equations, it's useful to write down the 5 variables, kinematic variables, and write down which values you know, which values you don't know, which one you're looking for. Right. So initial velocity is given. Final velocity, you don't know, because at 2 seconds, the ball hasn't reached the top. The acceleration is under free fall. So although the problem doesn't give you the acceleration being 9.8, you know that because it's free fall, it's negative 9.8 meters per second squared. And the problem asks you to find the final velocity at after 2 seconds. Okay, we don't know the how the displacement after 2 seconds. Once you've written down what's given and what you want to find, you now look at the kinematic variables. Okay, you don't know delta x. So any kinematic variable that contains delta x will be useless in solving this problem because you don't know what delta x is. You find that there's actually only one equation that you can use to solve for this problem. So you use that to find the final velocity, 10.4 meters per second, rounded to one significant figure because you have the least number of significant figures here being 1, 10 meters per second, consistent with the illustration we saw in the previous slide. All right, so for the second question, how high would the ball go before falling back down? We again use the same strategy. We write down what we know, initial velocity, and it's a free fall problem, so acceleration is automatically negative 9.8 meters per second squared. The problem asks us to find the displacement or how high before it falls back down. So as I've mentioned earlier, at the top of the object's motion, at the peak of its height, it will stop momentarily before going back down. So therefore, the final velocity will be 0 meters per second, right? So here you can see that the problem did not explicitly tell you that the final velocity is 0, but this is something that is part of the test, right? This is something that's part of what's being asked is for you to analyze the problem in such a way that you figure out that at the top of the object's motion, it will stop momentarily, and therefore the final velocity, which is the velocity at the top, will be 0. We don't know the time. Time is not given how long it takes for the ball to reach its maximum height. So when you're looking at your kinematic equations, then of course, any equation that contains time, any equation that requires you to input time will be useless in solving this problem because you don't know the time it takes to reach the top. And again, you find that there's only one equation you can possibly use. Okay. Right, so you use that equation to find the displacement or how high the object will go. You'll have to rearrange this equation to make delta x the subject or isolate delta x. You have here this rearranged equation, and then it's just a matter of substituting the numbers. Okay. Right. So for those of you who would like a refresher or a review on rearranging equations, you can go on the stream site. There's a slide. I put there a slide that gives step-by-step how to rearrange equations. And yeah, look at that. If you have further questions, please get in touch with me. We can arrange a special session to go over rearranging equations. In this course, we will of course be rearranging equations a lot. So knowing how to rearrange equations is a must. Right. So we have seen there. So before we proceed, are there any questions about kinematic equations or the example or so far? Nope. Okay. Right. So far what we have been talking about is motion along one dimension, right? Horizontal motion or just vertical motion as in the free fall motion. But sometimes objects can move in two dimensions. Projectile motion is an example of two-dimensional motion. We'll talk about projectile motion in the next lecture. But here's also an example when the velocity of an object is at some certain angle relative to the horizontal or vertical axis. So how to deal with motion in two dimensions, we'll need to know some sort of vector maths or vector algebra. Because vectors, we will often be dealing with displacement, velocity, and acceleration, which involve direction. And as we learn, whenever you have direction, that quantity becomes a vector quantity. So how do we deal with vectors? Okay, vectors are often represented in various ways. These are just some examples of how we write a vector. Often, yeah, you'll know that it's a vector if it's bolded or there's an arrow on top. Okay. We can also represent vectors as arrows where the length of the arrow is the size or the magnitude, and the arrowhead points to the direction of the vector. When we say negative vector or opposite direction, it just means, negative vector just means opposite direction. And because vectors contain information about size or magnitude and direction, two vectors are the same only if they have the same magnitude or same length and the same direction. Right? Okay. When we multiply a number to a vector, if the number we're multiplying to is positive, then the direction of the vector remains the same and only the length of the vector changes, as illustrated in this figure here. But if we are multiplying the vector with a negative number, like this -2 here, the direction of the vector flips because a negative sign means opposite direction. And the length of the vector will also change depending on the number you are multiplying to the vector. Meaning the magnitude of the vector changes. Magnitude is represented by the length of the vector. So this is so multiplication. So at least I think in this course we will also In this course, we will not do vector multiplication. So we will not do the cross product. We will do some kind of dot product, but I'll teach you that when we reach that point. At this stage, we're only just, when we're multiplying, we're just multiplying the vector with a scalar or a number, in which case either the vector lengthens or shortens, and then in terms of direction, either the vector's direction remains the same if the number is positive, or the direction of the vector flips if the number you're multiplying is negative. Okay. But what we will often use will be vector addition. We will often be adding and subtracting vectors. Okay, if the vectors are in the same direction as shown here, then we add the vectors to come up with a single vector here. If the vectors are in opposite directions, like these two vectors here, we subtract the vectors. Take note of our conventions, sign conventions. We will use the same sign conventions here. When we do addition and subtraction of vectors, we arrive at a single vector. This single vector is what we call the resultant vector. So resultant vector is essentially just the result, the vector that is a result of adding or subtracting. Okay. So I'll wrap up. So it's 4:52. So I'll wrap up this lecture by talking about, because the graphical method of adding and subtracting vectors. There are two ways for which we can add and subtract vectors in order to get the resultant vector, the graphical method and the component method. So we'll just have enough time to talk about the graphical method. The component method, we'll deal with that in the next lecture. The workshop questions don't have anything about vectors, so we should be safe. But yeah, but today let's look at how do we add vectors graphically. Graphical method means you have to draw the vectors in order to find the resultant. So say, for example, you have these two vectors, vector A and vector B, and you want to add them together in order to find the resultant vector. Vector A is pointing up, vector B is pointing to the right. When you add the vectors graphically, you're essentially joining them up sequentially head to tail, meaning you connect the tail of the second vector to the head of the first vector. So you can draw your first vector and then connect your second vector so that the tail of the second vector links with the head of the first vector. The resultant vector is then drawn from the tail of the first vector to the head of the last vector. Right? Important not to flip the vectors when you're adding, because you only flip when you have a negative, when you're subtracting, when the vector is negative. When you're doing graphical method, you'll have to measure the lengths of the vectors correctly in order to get the length of the resultant vector. I'll talk more about that later on. Now, when you're subtracting, you have again these two vectors, except that you are subtracting vector B from vector A. So similarly, you join them up sequentially head to tail, meaning the tail of vector B joins up with the head of vector A. So you draw your vector A. Okay. This time, because vector B is negative, okay, a negative sign means that you have to flip the vector. Hence, the direction of vector B is flipped here. but notice how the tail of vector B links with the head of vector A. Okay, it's only the direction of vector B that's flipped. And the resultant vector is drawn from the tail of the first vector to the head of the last vector. Okay. So you only flip if you are subtracting vectors. I think for this course, it's enough to know how to draw the vectors graphically to find the resultant vector. It's not a very efficient way of finding the resultant vector, because for you to find the resultant vector accurately, you'll need to draw each of the vectors with the correct length. And then for the direction, you'll have to measure the angle using a protractor. And that's why it becomes quite tedious to find the resultant of a vector graphically. Okay, so I think yeah, I'm trying to think whether there's, yeah, I think it's sufficient to know how to draw the vectors graphically and how to get the resultant vector graphically, but in practice, a more practical method of adding and subtracting vectors is using the component method. So in the next lecture, I will teach you how to add and subtract vectors using the component method. And we haven't really finished lecture 3, but that's okay. At some point, we will catch up. But I just want to lay down these foundation concepts because we will use them a lot, especially with vectors when we go to forces and Newton's laws. Having a solid understanding of vector maths will be very useful. So we'll deal with the component method next time. If you have any questions, feel free to pop them in the chat box. You're also welcome to stay for a few minutes to ask me your questions. But otherwise, I'll end the lecture here. You'll have the first workshop tomorrow online via Zoom from 10 to 12, where you will practice solving problems. So the workshop worksheet is already available on stream. You can download it if you want to go through the questions. You're welcome to do so. And then tomorrow you can ask me about the tricky questions, or you're also welcome to work on the worksheet tomorrow during the workshop. Okay, right, so I'll stop the recording.